All right, 6.3 counting principles. I want to make this as short as I can, but I also kind of love this stuff and want to show you all of the examples. So I'm going to try to be as quick as I can. So in this first example, we have 8 pieces of paper numbered 1 to 8. We're going to draw paper from the box, record it, put it back in, and then draw another one. And we want to know how many different ways can the total of 12 be obtained. So something plus something equals 12. I went ahead and listed this one out to save a little bit of time, but I could just think this through, common sense, until I figure it out, and here's what I have. So 4 and 8, 5 and 7, 6 and 6, 7 and 5, and 8 and 4. Because I am replacing the numbers back in the box. The only difference with example 2 is you cannot use 6 and then 6 because we're not replacing. So this one is the same, except we're not replacing. So we're drawing one and then we're drawing another. And because of this, there's only 4 different ways. Now, easy enough to do on your own when it's small numbers like that and you can think through. However, sometimes lists become more extensive and it's not feasible to list them out, but we still want to know how many ways there are. So, for example, how many different pairs of letters from the English alphabet are possible? Okay. It doesn't specify whether repeating is allowed, so we're going to assume that it is. I put a note there that you have 26 letters because I know some of us forget that. So I have 26 letters to choose from for my first number. And then I have 26 letters to choose from for my second number. So the total number of ways is 676. Now, if it were not repeating, let's say it was not repeating, then I have 26 letters to choose from the first time. I choose that letter. I'm not going to use that letter again. No matter what it is, it's there, it's out of the way. For the second one, I only have 25 letters to choose from because I have already chosen one. That's really the only difference there in that problem. So instead, I only have 650 ways to do that because I take out A, B, B, C, C, D, D, E, E, so forth. Okay? All right. Chugging right along. Telephone numbers. I find this one pretty cool. So our telephone numbers are 10 digits long as far as, you know, the school's is 859-381-3180, I think. Okay. Anyway, the first 3 are area code. The next 7 are local numbers. How many different telephone numbers are possible within each area code? Note that there are also 10 digits in our number system. So not just for a phone number, but like looking at your keyboard, notice there are 10 different digits that make up every other number for our entire number system. So I have 10 digits to choose from. But we have a special little note there that local telephone numbers cannot begin with a 1 or a 0. So phone numbers look like this: area code, and then the local number, right? So this area code cannot be 0 or 1. That means I have 8 options to choose from there because it can't be 0 or 1, but it can be 2, 3, 4, 5, 6, 7, 8, or 9. Okay. But all of the other spots, I can choose any of the 10 digits. So they can be 0, they can be 1, they can be 2, 3, 4, 5, 6, 7, 8, 9. They can be all of them. Okay? So our fundamental counting principle says that we just multiply all of those numbers together to figure out how many possibilities there are for phone numbers. So there are 8 million different possibilities. Uh-oh. That is wrong. So how many zeros we got? 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So okay. And so that is why we have the phone numbers that we do here in the United States, because it can cover 8 billion people. All right. Next, we're going to talk about permutation. So it's the same as the factorial, ideally. However, sometimes we only choose some, not all. So let's talk about what I'm talking or what I mean. The big important thing, so if you're a big highlighter, you need to know permutation order matters. Okay? So if we want to know how many permutations are possible for the letters A, B, C, D, E, F, could we list all of them? Sure. Could we think, there's a few ways to think about this, and this is where this video gets a little longer because I want you to think about them in all the ways. If I think about that this is 6 letters, I have 6 letters to choose from for the first time. I choose a letter, so I draw one out of the bag, I choose it. Then I have 5 letters to choose from. Okay, I chose a letter for the first one, I chose a letter for the second one. Now I have 4 still remaining in the bag to choose from. Okay, repeat that pattern. I then have 3 remaining in the bag, then 2. And then if all of the other positions are filled, I only have 1 other position that last one could be because we're not repeating here. Okay, so I would multiply that all together and be 720. Now, no one has time to list all 720 ways that those letters could be arranged. That being said, mathematicians are also lazy and they don't even want to write out this part. So they're just going to say that 6 factorial, so that is factorial, is 720 because that's the shortcut to state that it's the highest number multiplied by every integer down to 1 below it. Okay, horse race is the same way. But the difference here is we only have 3 positions. So 8 of the horses, 1 of them comes in first. Okay, so we have 8 to choose from that come in first. Then someone comes in first. We have 7 to choose from that could come in second, because whoever comes in first does not come in second. And then 6. So I multiply that together and I get 336 possibilities, assuming there's no ties, and also assuming that everybody has the same amount of chance of winning. Okay. So the factorial note should have been up there, so you don't need to write that down because you should already have it. There is a formula. Feel free to Google formula for permutations if you want to know where it comes from. However, we're going to use our calculator, more specifically Desmos, because I think it's a little easier. And for this example here where we had 8 and we had to choose 3 positions, it looks like this. So 8P3. And here's how we type it in Desmos when Desmos loads. If you are on a desktop or your Chromebook, you need to hit the little keyboard in the bottom left of your screen first for this to pop up. Then you hit Functions. You go to Stats in PR. Okay, and 8,3. Because you had 8 horses and you're choosing 3 positions. So easy enough. You may want to pause the video there to make sure that you get those steps down if you don't think you'll remember them. All right, so I always think this one's a fun one because I felt like in elementary school especially, I was always given those assignments that's like, how many words can you make out of the word underline, or, you know, whatever the word shall be. So I always thought, can I just start switching all the letters around until I just think about all the letters being switched, and then the ones that are words, right? So here's the math behind that. You take how many letters there are. So in this case, how many letters are there in banana? 2, 3, 4, 6 letters, right? So we do 6 factorial. We divide that by all the repeats. So notice that A is repeated 3 times. Notice that N is repeated 2 times, and then B is just once, okay? So it's divided by 3 factorial times 2 factorial. Then if you wanted to, technically it's divided by the 1 factorial 2, but 1 factorial is 1. Anything multiplied by 1 doesn't exist, so not a big deal, right? You can type that in your calculator as well. So opening Desmos back up. 6, it's also in stats, I believe. Oh, no, maybe I lied. Is it here? Yeah, there we go, it's right there. Okay, so it was in the keyboard area. So 6 factorial divided by 3 factorial times 2 factorial. So there are 60 ways to rearrange the letters in banana. Now, that is not to say that there are 60 words, because not all of those, in fact, most of them do not make words. But there are 60 different ways to rearrange them. Okay? All right. And then the other part is what's called combinations, where order is not important. So order does not matter. Those are your 2 big concepts. In Desmos, it's the exact same steps, just NCR. So for instance, in how many ways can 3 letters be chosen out of 5 of them? So A, B, C, D, E is 5 letters. And we are choosing 3 of them. So in Desmos, we're going to type it like this. Again, there is a formula. It's not as simple as the permutation one. So Google that on your own. But NCR 5, choose 3. So here, functions, stats, NCR 5, comma, 3. So there are 10 ways. Now that number's small enough that you probably could have listed all those fairly easily because there's only 10 of them. But it is possible that you forget one, right? All right. Maybe some of you know something about cards, maybe you don't. So a standard poker hand consists of 5 cards dealt from a deck of 52. So how many different poker hands are possible? This is kind of good to know if you ever think that once you hit 18 you would ever gamble. Okay, this is your teacher actually against gambling because I understand the statistics behind it and I understand how unlikely it is. Okay, so again, we're saying how many different hands could I have? We're not saying what cards dealt first and second and then third. We're just saying how many different ways could I be holding those 52 cards in my hand. So it's going to be 52, choose 5. And so, remember my steps in Desmos would look like this. So if you want to pause the video and try it yourself, go right ahead. I'm trying to finish up this video for you though. So that is 2,598,960 ways. And I'm going to stop there for the question, but just to kind of put that in perspective, so 2.5 million closer to 2.6 million different ways to get a hand in poker, but only very few of those win. Your stats aren't looking great there. So that's why the casinos can make the money from the people who play the poker. All right, last one quickly. Find the total number of subsets of a set that has 10 elements. So what we're saying is, what if they were all different shapes? Okay. I don't know that. Do I know 10 shapes? 3, 6, 7, 8. What else do I need? 9, 10. Okay. Subset means I could choose one of them, I could choose two of them, I could choose three of them, 4, 5, 6, all the way up to 10. How many different combinations could there be? So going back to the banana question here, these 60 ways means that we're using all 60 letters. What happens when I only use 5 of the letters? What happens when I use 4 of the letters? What happens when I use 3, 2, and 1? Okay, that's what we're talking about with the subsets here. So in this case, order does not matter. So we're going to use NCR. In banana, if we wanted to know, but order did matter, we would just use P instead of C, but the idea would be the same. So in this case, we're going to do, what happens if I have 10 and I choose 0 elements? What happens if of the 10, I choose 1 of the elements? 2 of the elements? 3 of the elements? All the way to where I choose all 10 of the elements. Well, however many number of ways that is, I would just add them together. And for the sake of this video, I'm just going to go ahead and say that it is 1,024 different ways. Okay, but yeah, I would add that all the way. So 10 choose 3, 10 choose 4, 10 choose 5, all the way up. And I could do, so obviously I would have each of them separate. I could have this as a subset. I could have this as a subset. You see what I'm saying? So that's for 10 choose 2 and so forth and so on. Okay, so video still went longer than I would like, but I think that this is super interesting and can apply this to whenever I'm just bored thinking about random things. So I really like this section, and hopefully you thought it was kind of interesting too.